that duplex there. Okay, does anybody have a question? So that's prokaryotic in a nutshell, transcription, initiation, elongation, and termination. Let's look at eukaryotic cells. First of all, y'all remember eukaryotic cells have 3 polymerases, 3 RNA polymerases. Polymerase 1 is responsible for transcribing the multiple genes that encode ribosomal RNA. Polymerase 2, which is the one that we're going to talk about the most, is the one that's responsible for transcribing genes that encode protein genes. There are also genes that encode some RNA molecules, but not the ribosomal RNAs. Polymerase 3 transcribes the genes that are also involved in protein synthesis, tRNA genes, and one of the ribosomal RNA genes, 5S RNA gene, also some of the genes that are involved in the small nuclear RNAs that are involved in processing primary RNA transcripts. We'll talk about those. But there are 3 of them. We can identify them, we can inhibit them. They are differentially sensitive to the poison that comes from amanita mushrooms. So when you go out in the woods, you see that red mushroom with the white spots, amanita. If you eat it, it's poisonous and kill you because it inhibits these polymerases. 1 is is less sensitive. 2 is very, very sensitive. So we at one time we used it to distinguish these. If you look at polymerase 2, this is the one we're going to talk about. It's a multi-subunit complex. It's from yeast. It has about a dozen subunits. As I said before, it's difficult to identify which subunits because you start, as you purify the proteins, you pull them away, and you just look for changes in activity. These seem to be there. And this guy here, these subunits out here, beta, beta prime, alpha, and delta. These are the enzymes. These are the main molecules, the catalytic part of that molecule. These other guys, these other things, these other subunits, which are all part of polymerase 2, some of them are found in all of the polymerases. You can see one is only found in polymerase 2. But anyway, there's a dozen subunits or so. And in polymerase 2, there are different types of promoters, which you can see the promoters. There are promoter regions that are recognized by different proteins. If you look at the promoters in many messenger RNAs, you can see that there are regions in here which are promoter regions which are recognized by particular proteins. Right? There is a TATA box, which is very similar. It has pretty much the same sequence. The difference is that the TATA box in eukaryotic cells is further upstream. Remember, the center of that box is minus 10 in prokaryotes. Here it's about minus 25. And whereas that other boxes, they have that TTGACAT at minus 35, these guys have a GC, a CAP in the box. And you can see where they're located. Most of these guys, the GC box, the CAP box, the TATA box, control the initial binding of RNA polymerase. Right? Now, remember that there's a difference in that TATA box. We talked about these promoter elements and being close to the consensus and increasing transcriptional rate the closer they are. But they have another very big function, and I can tell you about it actually. And if you go back to these guys, one experiment that's kind of telling. If you go back to this region here, if it turns out if you take this region here and you delete nucleotides, right? So delete a couple of those nucleotides, what happens is the transcription starts, rather than starting at the start site, which we call +1, and which usually, anyway, this starts at +1. It'll start at +3 or 4. So if you take 2 of these out, it starts at +3. If you take 4 of them out, it starts at +5. Right? So what that's telling us, what does that tell us about this region here? What is that doing? Anything at all? If you insert them in here, then it moves, if you insert nucleotides, put an insertion in there, then it moves this +1 start to maybe -3 or whatever. So what that says is that the TATA box is essentially not only in helping to initiate transcription, but it aligns the polymerase, it aligns the replication or the transcriptional complex, right? It's like a signpost. So where it sits is where, depending on where it is, and that's why that -10 is so well conserved. In eukaryotic cells, right, it's at minus 25 about. The Tata box is about minus 25. What's that tell you about the transcriptional complex? It suggests, doesn't prove it, but it happens to be right, that it's a much bigger complex. It has a much bigger footprint. And in order for that complex, remember, which has polymerase in there, to sit on this gene, sit on this DNA, and begin transcription at that site there, which is +1, right? It has to have that site further upstream into that complex. So anyway, the complex sits, this pretty much regulates where this complex sits, and these other guys here regulate the binding environment. All of these promoter elements, these are all different promoter elements, they're all called proximal promoter elements because they're very close to the gene itself. Within about 200 nucleotides or so, we call these things proximal. When a promoter element, and we'll talk about some of those later, is further outside, it could be way out here, it can be tens of thousands of nucleotides away. Those are known as distal promoters. Proximal promoters and distal promoters. The other thing to remember is these guys here, these are sequences, right? So those are in the DNA. But these proteins, OCT1, CPF, SP1, EBP, binding protein, these are proteins that recognize those sequencing bond. They have affinity. Okay, so we talked a little bit about the proximal promoter elements. There are what we call response elements. And these response elements occur promoters occur close to genes, close to the proximal. So they're proximal. They're close to promoters. They're responsible for the expression of related genes responding to physiological changes. So, for instance, there's what we call a heat shock element. This sequence here. This sequence is bound by a protein called the heat shock transcription factor. And what these response elements are, right, is our pieces of DNA bind with protein transcription factors, this particular guy, right, and induce transcription of genes under certain conditions. Why they're called response elements, right, is that they respond to some sort of a signal that is given to the cells. And these elements are also generally occur on more than one gene. So when a cell is heat shocked and is subjected to very high temperatures, it expresses a set of proteins that help it to get through that very high temperature process or period. So there are several genes that do that. All of those genes have these response elements due to their promoters. And so they respond to that. Kind of make sense? I'll show you in a minute. So here's an example of a gene. This is the metallothionein protein. Metallothionein is a very small protein that has 7 sulfhydryl pairs in it. And those sulfhydryl pairs are able to bind to one thing, heavy metals. Right? So they'll bind to heavy metals. This is a piece of that. This is a copy of that promoter element for that gene. You can see that here's the Tata box we talked about, the GC. That's the only one in here. So Tata and GC are those proximal promoter elements that bind to EBP and SP1. You can see that there's all of these other guys are response elements, right? So basal level, and these response elements are parts of can be enhancer. So this basal level enhancer, these are genes, these are regions. All of these regions, these are all part of the promoter. So what are they all doing? They're all promoting the binding of the transcription complex. So the function of all of these is to bind transcription complex to the promoter element. One of the reasons for showing you all of this is to look, remember we looked at the promoter for bacterial cells, Tata box, DPGACAP box. These guys have all of these promoter elements, which means that that regulation of transcription is much more complex in eukaryotes. It can be much more complex. And one of the reasons is because of all the different types of cells, and the other is to integrate many signals. So basal response elements, these guys here, basal level, there's always some of this metallothionein transcribed in cells. So when a protein binds to that, it's transcribed. The protein that binds to that called AP2. Metal response elements. If the cell is responded or is exposed to metals, toxic metals like lead, or cadmium or something like that, then it'll bind to a protein, and that protein binds to these metal response elements, these MRE guys here, the blue guys. So now we have proteins at more sites, increases transcription. Glucocorticoid response elements, right? So if your body produces a lot of glucocorticoid hormones, they bind to this, increase transcription of these genes. They can bind all together, they can be expressed, or they can be expressed at different levels. Your body can produce glucocorticoids in the absence of these metal response or heavy metals. So by having all of these binding sites, all these regulatory units, your cells are able to very tightly and very specifically regulate transcription of particular genes. So take the point of that. These guys that are close, notice these response elements are generally fairly close. Some of them actually fall, within what we call the proximal promoter, and all of them are close to 200 or so. So this is really probably would be considered proximal response elements or proximal promoter elements. Who has a question? Can't spend a ton of time on this. Okay. Now, what about transcription factors? I want to talk about initiations at one of these promoting regions. And one of the big differences between eukaryotic and prokaryotic cells is that prokaryotic polymerases, RNA polymerases, are able to recognize promoter elements. If you have, the holoenzyme that has that sigma factor, it's able to walk up that DNA and find a promoter. In eukaryotic cells, that's not true. If you have a polymerase complex that you isolate from the eukaryotic cell, the one that I showed you with 12 subunits, if you put it in a test tube of DNA, the eukaryotic DNA, it'll start transcribing at the end. Wherever the end is, it drops on the end and transcribes. It doesn't go down in the DNA to find a promoter. It can't. Eukaryotic polymerases cannot localize promoters. They need factors to help them. They're called transcription factors, and the ones that help to bind polymerases are called TF, transcription factors. The 2 refers to the polymerase, so these are transcription factors for polymerase 2, and they're labeled A, B, C, D, E, F, and so forth. And those labels, or those final letters, just refer to the sequence with which they were identified. So the first transcription factor identified for polymerase 2 is this guy here. Okay? Now the table shows you several of those. It shows you the number of proteins that are involved in each of these transcription factors. So transcription factor 2 has 14, actually 15 subunits in it because T3 is part of it. I'm going to go and I'm going to show you the sequence of events that occurs for these guys here. You can come back and